early stage company from Germany. So what we do is essentially we're building an optimization layer for clouds, a storage optimization layer for clouds. It's an NVMe-based block storage layer with an CSI driver on top of it. As such, it provides storage for hosts and containers. Using the NVMe-oF Fabric TCP initiator, we are tightly integrated into the Kubernetes ecosystem. The solution is fully containerized. The storage plane is entirely built on top of SPDK, and then we do have a control plane that provides services like CLI, API, deployment, monitoring, alerting, and so on. And generally, it's cloud agnostic, but at the moment we are focusing on AWS, and all the experiences that I'm sharing today are around that cloud. So control path. Let's start with that one. As I said, it's focused around Kubernetes. So typically, the Kubernetes workload would issue the request, the persistence volume claim, or resizing, or snapshotting, or cloning request to the Kubernetes control plane, from where it goes into our CSI drivers. There's a control part that communicates with our control plane. It does all the provisioning and volume lifecycle management there. And then there is a node part of the driver, which essentially triggers the connection to the particular storage plane from the Linux kernel, and then also exposes these volumes with particular file systems mounted into the containers. So pretty much standard. Storage plane can be local, meaning co-located with compute, or it can be also a remote storage plane that is connected via NVMe Fabric. So the data path, it's a direct, either NVMe directly onto the local storage plane, or then if it's remote, it's the NVMe-oF Fabric TCP initiator. So we have like this hybrid model where you can have storage plane nodes, storage nodes either locally in the cluster, in the Kubernetes cluster together with compute, or they are separated, disaggregated storage, and you can combine the both. Under the hood, we also have this connectivity to S3. S3 we use for disaster recovery and storage tiering, and then we also can pool EBS volumes. These are the block storage services in AWS. So I'll go through some concepts, basic concepts of architecture, and then I will get you some of the findings that we had on the performance side, particularly with AWS and SPDK, and then also some findings around running SPDK generally on AWS. That's the stack in the storage pod, in the storage node, if you want. So these are the different data services. So we expose logical volumes as NVMe Fabric namespaces via an NQN to the subsystem, to the Fabric. Below that, we have encryption and compression services, and then we do have distributed erasure coding, so meaning the chunks are distributed across the nodes in the cluster. And below that, we have a distributed placement, we also have quality of service, we'll talk a bit about, and then below that, all the NVMe TCP initiators. So essentially, each storage node is connected to all of the other nodes and all of the other devices in the cluster, which scales quite well using SPDK. So up to 1,000 initiators on a node are not really an issue. Distributed placement, so that's pretty, I would say, straightforward. So we have the extents on the logical volume that are actually mapped through to the erasure coding. So when you take an extent, we slice it into the individual chunks, create the parity there, standard parity erasure coding algorithms that we use, RDP for example, for parity 2. And then we use these individual chunks. They are, for example, 2 megabyte in size, and we place them in the cluster. We use a pseudo-randomized placement. If you're familiar with Ceph, that's a little bit similar. So we have a key, a multi-part key, and we map that to a storage ID in the cluster. We also use placement policies in that case, so we can say that should be on different racks, or in different, or should be oppositely located close to each other. And then also, this algorithm is not just a mapping, but it really takes care. So when we rebalance the cluster, that it's at the minimum cost, let's say. So rebalancing should be close to the theoretical minimum in terms of data movement. And then from there, we just use NVMe Fabric to send the I/O to the target device. Yeah, the mapping on the lower level, on the device level, it's pretty simple. So it's just a segment mapper. We have a pool of a free pool of segments, and we are just mapping the incoming data to these fixed size block segments, which is highly performant. It's just a few microseconds in the data path. We do have a metadata journal. So this metadata journal essentially stores information on a per segment level. It's really a journal, so it's crash consistent, it's power failure safe, and we compact this information every 10 or 20 seconds, where we basically take a snapshot of this metadata, store it back to disk, and remove the journal part of it. We do have information like a location, block level allocation map there. We have the placement map stored. And also, for example, for disaster recovery, we have a map to the write-ahead log where we know which position on the secondary storage the block has. And then we do last touch sequencing for cache evacuation algorithm to basically know which storage can be tiered out to S3. The journal, it works on 3 replicas. So each of those journals has a primary one locally and then 2 remote ones as replicas, compaction, and the write amplification of the journal is only 25% because we are actually collecting records into larger batches depending on the IOPS pressure of the system and moving them then together with the I/O. We use multipathing for high availability, so that's built into the kernel, means essentially the data as such is anyways shared, so we have a shared pool of data, as I explained through the placement. But then on top of that, we have the data structures storing information on the logical volumes and further down. So basically, those are instantiated in memory on more than one node, typically 3. And then if we have a pass-down event, basically moving that to the initiator will move it to the next node. And from there, we'll basically have a leadership acquisition. So the node will take leadership. It will first fetch remaining data from the storage to rebuild the data structures in memory that are required, and then start pushing it to its own journals. Asynchronous replication. So that's something that's important because on AWS, you don't have any type of disaster or zone level protection for your block storage volumes. So what you have to do, if you don't use a feature like ours, you have to basically replicate on the block storage level between the zones, and then you would have to have the compute on a high availability there. So we have this mechanism of asynchronous replication that goes directly into S3. It's behind maybe 500 milliseconds, 1 second in the good case, and so the RPO is really good. It allows us, because we use very high parallelism to write data to S3, to reach also very good bandwidth there. And so we are collecting data into like several megabyte objects and then storing these objects on S3. And in the recovery case, we can basically bootstrap in the reverse manner the whole environment and provide crash-consistent recovery across a number of logical volumes with a nearly zero RPO. And this whole thing also works for ransomware attack recovery because you can essentially lock the objects over a retention period, so delete and write protection. And then basically this log, it has also a compaction mechanism, but it has to wait until the time window is over. So basically within that time window, you are safe to recover with a near zero RPO from an attack. You have to find the right point in time, of course, to go to, but from there you can recover. QoS, so we also have QoS. It's basically simple feature. We are holding back non-priority I/O, so we're basically buffering it. If the queue depth gets too high, we'll just let through the highest priority, and then the rest gets arbitrated into priority classes, so we can give a very high, very low access latency for the priority I/O, even if the total IOPS pressure on the system is high. Auto-rebalancing, so the cluster has an auto-rebalancing feature, meaning that whenever, so there are actually three cases. So one case is you expand the cluster, you're adding nodes, can happen dynamically. It's a vertical scale out, meaning that we are rebalancing the capacity again in the cluster by moving data according to the placement algorithm, so that all of the devices are equally balanced after the rebalancing, and that gives us linear performance scalability. So basically adding nodes to the cluster allows us to scale at near linear performance, which is quite good, I think. And then the other cases are clearly device failure. So if a device is, or a node is gone for good, it will be migrated back, the data will be migrated back to regain full redundancy. And then also there is migration in case we have outage on some of the devices or nodes, and they come back. We also redistribute the data that is actually meant for these devices. And here are some findings on the performance and scalability with regards to SPDK and us on SPDK. But I think they're generally applicable for SPDK. So two things. Software performance, it's rather clear. So we measure the impact of our let's say, of our performance footprint on top of the raw performance of the hardware, network compute, and storage itself. So the net I/O access latency per queue depth that we see increasing by our software stack, we did measure separately. Then the total vCPU consumption per kilo IOPS effective, clearly. So how much CPU we burn to create 1 kilo IOPS, and then read-write amplification clearly is an important indicator. But then more interesting is actually system performance, because that's really an issue on AWS or generally on the clouds, and actually even the big competitors have that issue to give you a guaranteed SLA in performance or in reliability too, but let's focus on performance now. So really to understand what's the guaranteed sort of I/O access latency you get, and also the total IOPS that you can get from the system and the throughput, because we are not in control of the hardware, right? So this is still AWS. AWS does also not give us information on a lot of parameters there. They give very general information, but no details. So you have to measure you have to measure everything yourself, and basically create the baselines for compute. You need to really measure each nitro disk, get the IOPS under different I/O patterns, and the good news is it's reproducible. So once you do that, you have a baseline. So this mythically noisy neighbor, we don't see that much actually. So when you have really defined setup, you can rerun the tests and they will give you the same results, more or less, with some smaller exceptions, let's say. So based on that, if you have defined instances with a defined network bandwidth, you can really give SLAs to the clients, to the consumers, to the users, which is quite a significant step, I think. So yeah, that's on the system performance level. Some findings that we had, so read amplification is one, clearly. Write amplification is more or less on the theoretical minimum of the erasure coding. So if you have like 2 parity, then it will be on the 4 kilobyte random, it will be at least 3, and so on. And as I said, the overhead of the journal is really pretty low. Kilo IOPS, the approximate CPU consumption, it's 0.05 CPU cores per kilo IOPS, which, on the one side you think it's maybe enough. On the other side, when you compare to, for example, Ceph, you will see it's like 50 to 100 times better. So there is a big difference to other software-defined stacks, and the I/O access latency that's added is about 40 microseconds in the stack. And then on a system, so if we take, I mean, that's really a small cluster, so i3n, that's an instance type on AWS, 2x large, it's actually only like 20% of the instance, I think, or no, even less. And then we do that and create a cluster with 3 of those, and we get like 1.2 million IOPS on the read and about 600,000 on the write in a 1+1 and 8 gigabyte on the bandwidth of throughput. Scaling, SPDK scaling, so we also have some findings here. So when we talk about the single node scaling, so meaning increasing the number of vCPU on the node and looking at the overall development of the CPU per kilo IOPS, you will see that actually it's not scaling as well as it should be in SPDK. So we look at an architecture, I don't know who of you is familiar with SPDK, where we have user space polling mode, we have zero copy architecture. Well, to a certain extent, let's say on the TCP stack, that depends very much on the hardware. It's lockless and asynchronous messaging, so all of that should give you actually very linear performance scalability on a node level. It's not exactly like this, so it scales very well until about 16, maybe 20, maximum 24, but then you see some sort of saturation, and to be honest, we didn't finally figure fully out where it comes from. It's not memory bandwidth, the hit rates on the L1, L2 are very good, so it's not entirely understood, but this effect is seen. So what we do is really we focus on a bit of smaller nodes, not more than 2 to maybe maximum 4 disks per node, and try to just get more nodes. Yeah, this is about us scaling. I'll not go into too much detail here. I think it's not so relevant, but yeah, you have to really think about single-threaded design in SPDK. So anything that goes multi-threaded really becomes a problem because of the logs when you have a very high IOPS pressure on the system. So yeah, everything that we did is really based on keeping the threads as independent as possible. It's not 100% possible, but as far as it's possible, we do that. So we have no atomic reads or writes in the system, and we really looked at the L1, L2 caching. It has really high hit rates, and we're not moving too much data between between main memory and caches as far as that's possible. Yeah. So what's the good news when we take this node size, the defined node size, and then we add more nodes, like we have really linear scalability in the system, so that works very well. So meaning adding more nodes, that per node then it goes a bit down to maybe 75% of what the hardware can give you. But then when you add more nodes, you see really a linear curve. We didn't have the money to create 1,000 nodes, but what you can see is that the step from 10 to 20 is scaling very well linearly. And now a few findings that concern SPDK on AWS. So there are a couple of, let's say, assumptions upon which SPDK is built, and not all of them really hold true on AWS. So the first problem is queue-pair saturation. So whole SPDK is built on the assumption that you can reach the full IOPS performance of the disk with a single queue-pair. That's just how the architecture is. And it works with hardware. It doesn't work with the nitros. So basically, what you will see is that you need up to 3 queue-pairs, 2 to 3, to saturate the full disk. And that causes a problem because you have like you're single-threaded on the client side, and then you're mapping into that maps into one queue-pair on the initiator, right? So the Linux kernel has as many queue-pairs as cores, but then if it's one process, it's one queue-pair, and that one queue-pair goes back into the target, and then below the target, it's actually down the stack to the disk. It's still a one-to-one mapping. So basically, the problem that happens here is that with a single thread, you can't saturate that disk on AWS. So that's something you have to consider in your design, or it's just a limitation. Yeah, the number of Q pairs is another thing. So normally, and that's by the way also not on only on AWS, GCP has a similar problem. So normally per standard it could be up to 65K. All the hardware devices have more than enough of those. So you would never run into a limit, but SPDK assumes that you have at least one Q pair per core. But in that case, it's not possible because unfortunately the block storage, not the local disks, but if you use block storage, and we have a feature to pool block storage, you only have 4 Q pairs, and that's not enough because the node has more CPUs. So that's basically, yeah, resulting in either a segfault or, so basically here you have to work around. So that's a little bit of an issue. This mapping doesn't hold. You can reduce the core masks. You can be more specific to limit the number of Q pairs that you need because there are just not more. The hardware doesn't give you more. So that's one of the other findings. Yeah, the next one, write atomicity. So when you go into follow the NVMe standard and you query the disk, the Nitro, it will tell you it has 512 bytes block size. But then it has a write atomicity of 1, DPTU, or what's the parameter? So that's the identify, is it identify namespace or identify controller? I always mix them up, but anyways. So you'll find out it's just 1, so that would be a problem because you don't have 4 kilobyte write atomicity. But as a matter of fact, there's good news. So AWS implemented a separate feature outside of the NVMe spec, which is called torn write protection, and it will give you write atomicity depending on if you're on a Graviton or a x86. It will give you good write atomicity. Either 4 kilobyte is the minimum, but even 8 and 16 they have there. So that works well for us. So even if the block size is just 512, we get this 4K write atomicity that we need higher in the stack. And then multipathing, yeah, we had a little bit of a discussion with them because, you know, it's the NVMe-TCP multipathing. I think it's kernel version 5 something when it came in, but Amazon Linux 2 somehow it's not working. So they moved that module from the kernel. And well, first they denied it, but finally, yeah, they accepted it. But now they don't want to fix it because they're saying, well, you should anyways move to 2023. So, but yeah, so multipathing not working on the Amazon Linux 2. CPU architecture, that's also a little bit of a thing you have to consider because you have that core mask in SPDK. So basically, you're assigning.
Got a question about multipathing?
Yeah, sure.
So when you're talking about multipathing, so if I understand this correctly, you're presenting an NVMe device over Fabric's device out externally, right?
Correct, yes.
And then you're also talking to NVMe devices on the back end. So you're collecting them up and they're using them as your block storage that you're presenting.
Yeah.
When you're talking about multipathing, are you talking about multipathing that you're exposing to the initiators that are using you, or are you talking about multipathing that you're using to talk to the NVMe devices?
Yeah. Yeah. So the question is, are we talking about internal multipathing in our cluster, or are we talking about multipathing facing the client? I'm talking about multipathing facing the client because internally we use Rocky anyways, but if we run on compute and we have to face to the client, we depend on the operating system. And but this is not the MPIO, this is NVMe Fabric multipathing. I mean, yeah, so yeah, that's exactly the problem.
Could you repeat the question again?
So the question was about multipathing. So which type of, or where does the multipathing take place? Is it internally in our cluster, or is it basically phasing at the fabric level where the clients connect into our system?
And you're talking about the latter.
Yeah, we're talking about the latter, exactly. Yeah. So CPU architecture. So the little bit of a problem we have here, because we have this core mask on SPDK, so we need to say which cores we are assigning into SPDK process, and that's important because they will always be busy afterwards due to this user space polling mode. and then also within that core mask, you will assign certain cores to certain tasks, to certain threads. We have quite a sophisticated core mask, and now the problem comes in. On ARM, everything works fine because they give us one vCPU, one core, but on x86, they give us one vCPU, one hyperthread, and that's a problem because if the other hyperthreads are busy, they will have a noisy neighbor. So you need to be very careful to assign the core masks for SPDK in a way to pair the right threads into the same cores and then basically treat them as one core, because otherwise you will see nasty effects when compute workload comes in. So yeah, that's the only thing about it. Otherwise, yeah, everything good here. The only thing, performance profiling. So we use vTune, and vTune doesn't work very well on AWS. So we made it work on the large bare metal, but it's a little bit of a pain, and it doesn't work on any of the virtualized instances, not to the degree we need it. Yeah, I think that's pretty much it, I guess. So open for questions.
So I was curious how much encryption is important to your customers in the cloud.
Well, encryption is important. So I mean, they have. So sorry, yeah, I'll repeat the question. So the question is how important is encryption for our customers? So encryption is, of course, a big topic. EBS gives you encryption, and this is based on KMS. So this is basically user-managed keys, if you want. And we do the same thing. So basically, we accept the key through KMS coming in. It's in memory, and it's on the logical volume level. So that's how we do it.
So it's at rest.
No, it's inline. So it's happening when, so it's inline, it's on the hot data path. Yeah. So
you're running TLS on the connection?
You mean TLS now, or you mean, because I'm talking about logical volume encryption now.
Okay,
so TLS is a different story, yes, that we also have. This is between the host and the storage nodes, right? So this is TLS based, and also between our control plane and the client. But yes, within we use logical volume encryption. I don't know which one, but it's pretty much the standard SPDK one, AES, something. Yeah. Mm-hmm.
Yeah, I was just going to ask whether you reached out to the SPDK community about what being able to scale beyond 24 cores.
Yeah, we didn't do that yet. The question was if we discussed the issue of scalability with the community. We didn't do that yet. No, that's probably something to do.
They're pretty responsive.
Yeah, we are in contact on other issues. We went to the user conference, but yeah, not on this topic yet. Mm-hmm.
So today they have AWS Connect. Is that your solution? Is it interop with AWS Direct Connect?
So the question is our solution compatible with AWS Direct? Is that right?
Yeah.
Well, in general, there is no concern. The question is on the latency. So you're talking about which feature? Because typically the cluster has to be deployed on a single availability zone. It doesn't make sense due to latency because this is performance storage, right? So we can't cross the zone.
Part of the transport.
Yeah, if we talk about that, yes. So if we talk about, for example, asynchronous replication recovery, yes, that's compatible, yeah. Mm-hmm.
A couple of questions about encryption. If I understood you correctly, SPDK, is that the control for performing encryption?
Yes. Yes. So it's not at rest, again, so it's on the hot data path. So the question is SPDK in charge of encryption? So the answer is yes, SPDK is in charge of encryption. So there is a software a defined encryption module in SPDK that we are using for that purpose right now, and it sits on the hot data path. But the key comes from outside, and through the Kubernetes ecosystem and AWS, it's handed into the SPDK, and there it's held in memory, so we never store the key.
Okay, are you familiar with the new requirements for post-quantum cryptography? Because AES originally had 128, 192, and 256-bit keys. And now with the new requirements, it is 256 bits only. So the question is SPDK going to upgrade to use only AES encryption with 256-bit keys?
So the question is if I'm familiar with the encryption standard post-quantum and the move to SHA 256 on the AES encryption. Well, I've heard about it. I wouldn't say familiar. About SPDK, I can't answer this question. I don't know. I would have to check with the community, but I guess if it's a requirement coming up, somebody will have to do it.
Okay, I'll talk to you after the meeting.
Yeah, sure.
Question on the data placement and figuring out from the host,
Yeah.
like where to connect. I didn't quite understand where exactly that kind of demarche is happening and whether the host actually has to have multiple NVMe or fabrics connections to the backend storage nodes, or you mentioned the logical volume is your logical volume is somewhere in the middle. So
I will just try to go back and show this slide in the beginning. So, yeah, in fact, so the question is the connection, the NVMe fabric connection, where does it terminate and where is the multiplication, the distribution happening? So basically, the host connects one logical volume via one connection to one or multiple storage planes. Multiple storage planes, that would be the case if we use high availability because we need it for multipathing. In that case, multiple storage nodes would expose the same logical volume through 2 or 3 different connections. Connections are, if you use node affinity and if you have a local storage plane, preferably local for reasons of access latency, but also can be fabric. So the next storage node, if the next storage node is not local or if it's full, it can be another one. But all the, let's say, distribution happens then from there. So basically, we have like 2 hops. So ideally, we have more or less 0 hops because the data can be read from the storage plane if we have affinity. But in the worst case, let's say we have 2 hops. So 1 hop to the storage plane and then another NVMe fabric connection to the actual data source.
another question on the cluster rebalancing.
Yeah.
Have you measured, how much of a overhead that might cause in terms of the network data movement in the backside?
Yeah, I mean, so it depends, of course, how much you add and at which. So the question is how much overhead the rebalancing of the cluster causes. So we executed at larger data chunks at a lower priority. So basically, we give the client I/O higher priority on that. But it's distributed. So when we need to balance data from multiple existing devices to 1 or 2 new devices, we run that in parallel. It's basically bound by either the network or the capacity of the device, the performance throughput of the device that you're adding. So
there isn't like a separate network for that in the backend?
We do not separate the networks. I mean, it's hard on AWS because you can virtually segregate it, but physically it's the same anyways.
The data placement map, is that on a separate volumes?
The placement map? No, so first of all, it's pseudo-randomized. So basically, you don't.
What was the question?
So the question was if the placement map is on a separate volume. So the placement is first calculated just by an algorithm, right? So we know already where it's placed. But then, if we store the placement, it's in the metadata journal. So this is a partition on one of the or multiple of the devices on the local node, and then also on 2 additional nodes. So we have usually 6 copies of the metadata to be recovered in case 1 or 2 nodes go down. But it's physically, we don't usually waste the complete device for that because it's just a small amount of data. So it's a partition. Any more questions?
So when you're doing the rebalancing, do you see a dip in your I/O performance?
Well, I mean, if you're on max IOPS, yes, you will see something, of course. So the question is, sorry, yeah, the question, the question was if we see a performance dip on rebalancing. I mean, again, we don't see a latency dip on the high priority I/O, but of course we see a total decrease in IOPS and throughput that is consumed by that. That can be, it's adjustable depending on how long you want to wait, between 5 and 20%, depending on the size of the cluster. Yeah. But if it's really something that we can adjust. So if you want to, if you're not like adding permanently, expanding the cluster, you take a longer time to rebalance, it's fine. You don't feel it, the performance impact. Okay, so if there are no more questions, thank you.